An important sign of an approaching magnetic reversal is how sunspots behave during solar maximum. As the sun approaches the equator, sunspots become more frequent and visible, indicating that the magnetic field is becoming more unstable and ready to reverse. While we're on the subject, let's take a closer look at sunspots. The sun's magnetic field lines are twisted and tangled due to the differential rotation that occurs when the sun's equator rotates faster than its poles. The colder, darker areas that can be seen in sunspot images are caused by zigzagging lines across the sun's surface, which disrupt the convective movement of hot plasma from the sun's center. Sunspots are not only dazzling solar phenomena, but they can also occasionally release powerful coronal mass ejections, CMEs, and solar flares. These events release large amounts of energy and charged particles into space. If aimed at Earth, they can disrupt power grids, satellite communications, and endanger astronauts in orbit. Additionally, increased solar activity can enhance auroras, but it can also increase radiation levels in the upper atmosphere. While we're on the topic, let's look at the differences between CMEs and solar flares. Both are massive dumps of solar energy, but they are very different. Solar flares are short, powerful bursts of radiation caused by magnetic energy released from sunspots. They often release massive amounts of light and energy in the form of ultraviolet and X-rays. Think of them as bursts of heat and light, like a massive explosion on the surface of the sun. Coronal mass ejections, on the other hand, are massive explosions of magnetic fields and solar wind from the sun's corona. Think of them as giant bubbles of gas and magnetic fields being launched into space. During a coronal mass ejection, billions of tons of solar particles are ejected into space at extremely high speeds. Although coronal mass ejections and solar flares are related, they are not the same thing. Solar flares can occur on their own, but sometimes a coronal mass ejection can accompany a particularly strong solar flare. Solar flares do not always lead to coronal mass ejections. From a risk perspective, solar flares are relevant because they can disrupt radio communications and navigation and pose a serious risk to people in space due to their high radiation content. However, coronal mass ejections can cause geomagnetic storms that disrupt satellites, power grids, and navigation systems. They can also enhance auroras, but they also pose a serious threat to Earth's infrastructure and technology. Another thing to keep in mind is that periods of increased solar activity increase the amount of high radiation reaching Earth. In particular, spacecraft such as satellites can be at risk during periods of increased solar activity. Charged particles from the sun can destroy electronic components, disrupt communications, and even change satellite orbits. In addition to damaging technology and infrastructure, what other dire consequences could befall Earth? Earth's atmosphere is not directly affected by changes in the sun's magnetic field, but it can be affected by changes in solar activity. Changes in solar radiation can affect weather and atmospheric conditions. For example, some studies have shown that increased solar activity could lead to a slight warming of Earth's atmosphere, which could exacerbate climate change that is already occurring. Could the aurora borealis be the only good thing that happens to us on Earth? This amazing intensification of light is probably one of the most noticeable results of increased solar activity. The interaction of the sun's charged particles with the Earth's magnetic field and atmosphere creates this natural light phenomenon, also known as the northern lights and southern lights. We often read about it, but the northern lights can also be seen in Antarctica. The aurora borealis can be seen at lower latitudes and is more common during periods of high solar activity, making for a spectacular nighttime spectacle. But beyond the amazing auroras, there are some more surprising aspects of a solar reversal that can occur if we aren't prepared. The potential for geomagnetic storms is one of the major hazards associated with a magnetic reversal. Such storms occur when the Earth's magnetic field interacts with the solar wind, which is filled with charged particles. In severe cases, they can cause widespread power outages and damage. One such event occurred on the morning of September 1, 1859. As was often the case, astronomer Richard Carrington used his telescope to study the sun. But what he saw that day went down in history as the first solar storm. At about 11:18 a.m., Carrington noticed a bright flash of white light coming from a cluster of sunspots. This event, now known as the Carrington event, marked the beginning of the largest geomagnetic storm ever recorded. Carrington witnessed a powerful solar flare, a massive burst of radiation caused by the release of magnetic energy stored in the sun's surrounding material. The flare was so powerful that it made Earth the target of a massive coronal mass ejection, CME. The coronal mass ejection reached Earth 17.6 hours later, a very short time considering that the Sun is 93 million miles away from Earth. When the coronal mass ejection reached Earth, the magnetosphere reacted with solar particles, causing a massive geomagnetic storm. Auroras reached as far south as the Caribbean and were visible in the United States. Telegraph systems were knocked out and some telegraph operators were electrocuted. If the Carrington event occurred in modern times, it could cause massive damage to satellite technology, power grids, and communications networks. Could such a solar event lead to a global catastrophe? The answer may be yes. Scientists continue to monitor solar activity and predict future solar storms to better protect us from potential damage. However, as the sun's magnetic field continues to evolve and change, we must remain vigilant about the potential impacts of solar activity.
The sun has recently become one of our primary power sources, and a remarkable change in the polarity of its magnetic field is about to occur. This phenomenon, which occurs periodically and mostly in the middle of the solar cycle, has profound effects on us here on Earth. Surprisingly, the sun may soon pose a serious threat to the world, bringing complete chaos and death to all life. As you will know, the sun's magnetic field is generated by the movement of charged gas within the sun, the solar dynamo. Over time, the sun's convection changes and deformations cause this magnetic field to become more complex and rearranged. Eventually, the North Pole becomes the South Pole and vice versa, completely reversing the magnetic poles. So can we break down the entire cycle and see the sun in more detail? The sun is made up of plasma, which is mostly hydrogen and helium atoms, a mixture of free electrons and ions that are not bound to other particles. The radiation zone and the convection zone surround the central region of the sun, which is divided into several layers. The most important region of the sun is the center, where nuclear fusion converts hydrogen into helium, releasing enormous amounts of energy. The radiative zone, located above the core, is where radiation is used to move energy outward. Photons are absorbed by the solar plasma in this region and re-emitted, slowly moving energy outward. The convection zone, the outermost layer of the sun's interior, is where convection transfers energy. Convection occurs when hot plasma rises to the surface, cools, and then sinks back down. The T-line, a narrow layer between the radiative zone and the convection zone, is where the solar dynamo mechanism primarily operates. The asymmetric rotation and shear flow of the sun, which are important for generating the magnetic field, occur along the T-line. It is interesting to note that the sun does not rotate like a rigid body. Instead, different regions of the sun rotate at different rates. This is called differential rotation, with the equator rotating faster than the poles. The magnetic field expands as a result of differential rotation, stretching and twisting of the field lines. The sun's magnetic field changes during the solar cycle, which lasts about 11 years and ends with a pole reversal. This cycle, which consists of several stages, is powered by solar power. At the beginning of each solar cycle, the sun is in a state known as solar minimum, a state with few sunspots and little solar activity. The north and south poles are usually distinct, and the magnetic field is simply bipolar. As the cycle continues, more sunspots appear. Explosions of magnetic activity within the sun are associated with sunspots, areas of extreme magnetic activity. Over time, these sunspots migrate toward the equator and pair up with opposite magnetic polarities. The sun reaches solar maximum, a time of maximum solar activity during the middle of the solar cycle when the frequency of sunspots, solar flares, and coronal mass ejections, CMEs, is highest. The magnetic field becomes extremely distorted and complex due to the constant twisting and shearing caused by differential rotation and convection. As the solar maximum subsides, the magnetic field reorganizes. The Earth's magnetic field gradually changes polarity, changing the North Pole to the South Pole and vice versa. The The evolution and reorganization of the solar plasma field contributes to this cycle as the rearranged and entangled magnetic field lines reconnect. The Sun goes through a phase of decreasing activity after the polar reversal, reaching solar minimum. The cycle eventually ends when the magnetic field realigns. We are currently in solar maximum, and the Sun's magnetic field is ready to reverse. At this stage, some solar activity can be expected, which can be both dangerous and exciting. However, the reversal of the solar magnetic field is not an unexpected reversal, but a continuous cycle. The magnetic field of the Sun fluctuates throughout the solar cycle. It is currently in its most distorted and chaotic state. Eventually, it will tilt and begin to rearrange itself, causing catastrophe. So, when does the Sun's magnetic field change polarity? Scientists use a variety of instruments and techniques to monitor the Sun's magnetic activity. Powerful telescopes on Earth and in space can produce extremely detailed pictures of the Sun's surface and sunspots. The Sun's magnetic field is measured over time by instruments such as the Solar Dynamics Observatory